we've seen at least one situation in which vectors were applied to projectile motion. That situation, you recall, was where the object came off in a horizontal direction with no vertical component, and that's been the case with all the projectile problems that we've looked at so far. In this case, we're going to assume that an object rolls down a ramp and the ramp has an upward curve at the end, and the object comes off with some initial velocity that's no longer exactly horizontal. Now in this case, we have to specify the angle at which the object comes off. We'll say that angle is 30 degrees, and let's assume that the object comes off at 5 meters per second. Now there are other ways an object could attain a 5 meter per second velocity at a 30-degree angle. It could be thrown, it could be shot out of a gun. It doesn't matter how the object gets that velocity. What we're interested in is the motion of the object between the instant it leaves the ramp and the instant it strikes the ground. Now we're going to assume the ground is 10 meters below. Forgive the fact that the arrows don't come all the way up and go all the way down, but this 10 meters here really refers to the distance from the bottom or from the ground up to the point where the object leaves the ramp. Okay, how are we going to analyze this situation? Well, we know that when a projectile is in free fall, if we ignore air resistance, the x velocity is going to be constant, and the y velocity is simply going to be uniformly accelerated motion, or the y motion will be uniformly accelerated at 9.8 meters per second squared toward the center of the earth, or in this case toward what we would think of as the level ground. From the angle and the initial velocity, the magnitude of the initial velocity, we can easily determine the x component and the y component of that initial velocity. Have an error here. This says 0.443 meters per second. I'm going to extend my equal signs there and plug in my decimal there, and that's going to be more appropriate. In any case, we calculate the x component of the velocity by multiplying the initial velocity by the cosine of the angle, and the y component is going to similarly be calculated by multiplying the initial velocity or initial speed, magnitude of the initial velocity, by the sine of that angle. We obtain initial x velocity of 4.33 meters per second and initial y velocity of 2.5 meters per second. The other thing we know about the horizontal motion is the acceleration is 0, and so that the final velocity is the initial velocity, etc. We have a constant velocity situation. We can't at this point determine the time interval dt or delta t over which the object is in horizontal motion with this velocity, nor can we determine the horizontal distance. Okay, so we're still left with distance and time excuse me, with distance and time unknown. We can analyze the y velocity, or the y motion though. The initial velocity we've already calculated. The acceleration, of course, is negative 9.8 meters per second squared, and the total y displacement is negative 10 meters. Now there's often some confusion. I mean, the y displacement, we go up to some maximum height and then we fall, and people often want to break the motion into two segments, one while the object goes up, the other while the object goes down. We can do that, but we don't need to do that. The equations of motion were derived with no provisions on what these velocities and displacements are. The idea is that the net displacement from here to here is going to be negative 10 meters. So that we're simply going to use that as the net displacement, and we're going to get a very sensible answer out of these assumptions.